do with you in just a second.
Just making some cashew butter first.
Yeah. All right, let's take a moment. Some news up there. Adrian, good to see you. Let's take a moment of mindfulness. Something a little different, kind of profound, simple. Just for the next couple minutes, close your eyes, and without relying on the models you have built, where is the edge of your body? Based alone, solely on sensation. If that's too much, can you discern the shape of your hand? If you had never seen your hand, what would the sensation tell you its shape is? Attention and focus you put on this, the more ineffable that boundary becomes. As pleasurable as that is, let's just gently come back. Talk about some calculus. Speaking of which, I have something for you. And I didn't want to give before the moment of mindfulness to completely destroy that. I have your exams. So, no, don't be scared. It's all good. So, corrections are due next Monday. The details for corrections are up on World Class. Again, I have a precise thing that I want for that. Please pay attention to that. Failure to comply with my authoritarian nature will result in severe punishment. No, it won't. It will certainly result in less credit, though. So, you can earn back 50% of what has been lost on this exam. I did grade pretty rough because of that. Each problem was 11 points. And so you can gauge what you got out of that. Monday, starter class, yes sir. That should be easy. Don't hurt yourself doing that. Thank you. Of course, you have to have lost more than 1 point to turn them in. So, alas. Cal is sick today. Juan is over here. Juan's going to do it anyway. This one's Claire. It's probably nervous, but shouldn't be. Mr. Alex. Merci. Sheet. Check that over. Definitely one thing to make sure is that I didn't take off more in total than should have been taken off. Please check that to make sure. you have any concerns or anything, we can talk about it on Friday, or you can shoot me an email, we can have some kind of correspondence about that. My office times are pretty locked up this week because I'm doing advising, so I don't have a lot of free time. Because I taught freshman seminar last semester, so I've literally got a barrage of freshmen who need all sorts of things beyond just simple, here's what I'm taking next fall. This makes sense? Good? Cool, wonderful. All right, so that would be the thing that I put up here. Corrections due, start of class on Monday. Make them nice, make them pretty, make them right. That's the way to roll. So we are starting a whole, kind of a short section. Blue. Starting a very short section. In fact, the exam for this section is going to be an online Webwork assignment, which is pretty cool, right? I mean, like, it's your chance to get a perfect exam. It's going to be just like our normal Webwork. I'm going to give you an assignment. You're going to have infinite chances to get everything right, and you're going to have a reasonable amount of time to do so. So this next exam, the exam 3, which will be maybe in like 3 weeks, that's your chance to ace an exam, get a nice solid 100%. There'll be a small written component as well, like a one problem that you have to write up nice and turn in. So this Webwork here is on the first application of derivatives. Part 1, Lhopitals Rule. This is the most challenging, I think, in some ways, because we're gonna go back to like day 1 and go in deeper than we did before. We're gonna talk about limits again. So this is all about limits and a very particular situation. So let me give you the problem here. There's really kind of 2 problems that we want to deal with. 2 problems. One is we have a limit where x is going to some value, and we've got a function divided by another function. What's the first thing we always did when we were evaluating limits? We had a 1, 2, 3. What was the first thing? Simplify? Even before that, maybe. Like, what do you hope you can just do?
Plug and chug.
Plug and chug, right? Then simplify, Nina. Yeah, absolutely. So what we hoped is that we could just plug in the limit point, and that would be good. And that was good whenever these values weren't 0 over 0, right? Or we weren't dividing by 0. So what happens if this is 0 over 0? Then we would go to Nina's plan, factor, cancel, hope for the best. Sometimes that's not an option. For example, in a case like this, there's no factoring to be done. Now, there are some folks in here who might try to factor it because they think sine is a thing by itself and think that's sine times x. But no trig function can ever be factored. Just keep that in mind. That can't be factored, log can't be factored. This is an of statement here. So with this one, sine of 0 is 0. We get 0 over 0. How the heck could we possibly do that? Well, Lhopitals Rule is going to make it a piece of cake. Otherwise, you'd have to go to like Desmos. I think this is how we were doing things like this at the beginning of the year. Go to Desmos, look at the graph, or type it on your calculator. Let x be really tiny. What is the value of top and bottom? And then the other problem, so this is problem 1. Problem 2 is this one, where we have the limit and we're actually letting x become larger without bound. Here's kind of a new notation. We haven't ever written this before. But what this means is as x becomes large without bound. In some sense, you're going to infinity on the right and wondering what the output value is for a particular function. We'll get into that in a bit. But this is all about horizontal asymptotes. So just really quick, let's say I graphed out, here's y equals f of x over g of x. Just so you see what I'm doing, before we even talk about it. Let's say the graph did something like this. And this is 3 right here. Then if this is the graph of f of x over g of x, the limit as x goes to infinity is 3. That's what the output is approaching as I move further and further out this way. So for this one, we would say here the limit as x goes to infinity, f of x over g of x equals 3. Just an intuitive start to everything. Hopefully intuitive. All right, so let's talk about Lhopitals Rule. So in Lhopitals Rule, we've got something like this going on. I've got a function that's going to 0 at a point divided by another function that's going to 0 at a point. So that would look like this. Let me get multiple colors up here, actually. So let's say f of x looks like this. So there's y equals f of x. And then this point here is a. So now I've got f of a equals 0. So note that. And then I've got this other function, g, doing something like this. This is y equals g of x. And note that g of a is equal to 0. We are interested in the limit of the ratio of those two things. To sketch that out would be really painful. It's not going to be helpful, or I don't think it's going to gain you any insight. But that's the setup. So, what? Yes, sir.
What do you mean by ratio? Like, I know what a ratio
Oh,
is, but ratio
this.
is two things. Okay.
Yes, yeah. So we're going to study. Yeah, let me write out. We want, let me be more clear, Alex, to make that solid. We are interested in the limit as x goes to a of f of x over g of x. We know we can't just plug in a because then we get 0 over 0. We might be able to factor, we might not. So how could we do this? Well, check this out. What we're going to do is we're going to, since the limits are all about what happens when you're near the point, we're going to do the thing that gives us an approximation of the functions at a point, the tangent line. So the limit here of these two ratios should be the same as the ratios of these tangent lines. So let me put these here. So those are the tangent lines. This one here is the linearization of f. Oh God, we don't have any good notation for that. But it's the linearization of f of x. Let me write clearly. F of x at a. And then this one here is the linearization of g of x. In other words, just tangent line. Don't let that word throw you. Of g of x at a. And so we're going to replace each of these functions with their tangent line approximations. And then take the limit. Because the tangent line acts like the function near the point of tangency. So this should be equal to the limit as x goes to a. How do I find the equation of the tangent line? Well, remember, it goes like this. It should go like that. Lots of folks got that right on the exam, so that's good, but that's the equation of the tangent line. This is equal to the function, its derivative at a point. This is equal to the actual value at a point. So here, if I had x naught equals a, and I'm looking for the equation of the tangent line at a, it would look like this. Y equals f prime at a, the slope, times x minus the x coordinate, plus the the y coordinate at A. So I'm going to replace the top thing here with f prime at A over x minus A plus f at A. And I'm going to do the same thing for G. Equation of its tangent line would be its slope at A times x minus A plus G of A. Let me stop for a second. Make sure that you're following along while I sit in this filth down here.
That 45-year-old carpet.
Oh, absolutely. Can you imagine? No, let's not. Let's
This
bring it
carpet
out.
was originally white, you know.
I believe that. Yeah. I've spent 15 years sitting in this filth, so a lot of it's mine. Fair enough, you know. And is there anything I could simplify here? So, are there any value? Yeah, Nina.
On the bottom, is that G prime? Oh, never
Yes, ma'am, it is. Yeah, good question.
Could you do the x minus a on both sides, or since it's attached with addition, you can't really?
So yeah, so that's right. Good. I'm glad you stopped yourself, Alex. Can't cancel yet. But are there any values here that I can plug in? What do we know about f of a and g of a?
0.
They're zeros. That's the assumption. So we are literally assuming. So we assume that f of a and g of a are both dead at that point. So this is 0 and this is 0. So this limit becomes limit as x goes to a of f prime of a over g prime of a times x minus a over x minus a. Now, Alex, now I can cancel.
Sure.
Because that's just, this is multiplication here, so cancel that. And these are constants. And this is going to be the case provided this bottom thing isn't 0. If g prime of a isn't 0. And when it is, we'll deal with that. We'll talk about how to deal with that. So let me write this up. Here's the summary. Lhopitals Rule. And then we're just going to practice this literally for the next couple days. So, Lhopitals Rule says the following. To find limit as x goes to a, f of x over g of x, when the top and bottom are both 0 at the limit point, try instead the limit as x goes to a of the derivative of f over the derivative of g.
So could we do sine of x over x though?
We can, we'll do it. Yeah, we'll start right there.
So cosine x over 1.
Look at you. Doing freaking calculus in your head? Yeah, beautiful. Yes.
Over there on your notation, you
Yes,
have
ma'am.
f prime of a over g prime of a if g prime of a is not equal to 0.
Thanks, Nina. Yep, good call. Correct. Yes, ma'am. If this turns out to be 0 over 0 again, we're just going to keep L'Hopitalin. And we keep L'Hopitalin until we have something that works. And we'll see that in a minute. So let's use this. I like Alex's idea. Let's go back to limit as x goes to 0, sine of x over x. So first thing I note is that's 0 over 0, so I can't do it. That is the only time this or this is the only time you can use Lhopitals Rule. We'll get to that in a bit. But the way I write this and the way I'd like you to write it is when you make the transition using Lhopitals Rule, please note that you are L'Hopitaling. Take the derivative of the top over the derivative of the bottom, and now try plug and chug again. So at every step of the way, I'm just going to apply L'Hopital's rule. Notice this isn't the quotient rule. It's what you wish the quotient rule was, but it's not the quotient rule. It's simple. Derivative top over derivative bottom. So this, I plug and chug. Cosine of 0 over 1. Cosine of 0 is what? 1. So this limit is 1. Let me point out something a little interesting here that I didn't know necessarily we were going to talk about, but if I say this, that actually means something really useful. It means that when x is a really tiny magnitude number, really close to 0, so like when x is 0.01, sine of x over x is approximately 1. So let's write that out. When the magnitude of x is small, close to 0. These two things are the same, i.e. sine of x is approximately x. So I can interpret this limit as something that's somewhat useful to me. I need a calculator, friend. And you need your calculator in radians. What is sine of 0.01? Can someone do that for us, everybody? I can do it, and it doesn't look like anybody's actually moving their hands or anything.
Oh, I don't
So
think I have
that's okay. What's that?
I don't think I have one.
You got a phone?
I do.
You got a phone?
I just don't bring my calculator because we don't really use them. So
No, exactly. No, fair enough. I get that.
tell us not to use them. So.
You got yeah. I know. So get your damn calculator, turn it on its side, get your nice, beautiful scientific mode. I see Adrian's helping me out here. So I'm gonna step into 0.01. Ooh, shit! Can't even use the calculator. I use it so seldom. Whoa, am I entering the wrong number? Oh, I think I'm in degrees mode. If you don't get something that's close, you are in degrees mode. Wow. Okay. There we go. So Adrian, you tell me if you got the same thing. I get 0.009999983. Something like
I'm
that.
just trying to remember how to change back into radians.
Okay, fair enough. Olivia, you got that? Awesome. So we see they are not equal, but they're hella close.
I did it and I got this. It's kind of the opposite number.
You are in degrees mode.
How do I change that?
Hit the, see the rad, see the
Yeah.
button that says rad, hit that, now try it. This is good, it's calculator exploration day.
On the phone.
It work?
Yep.
Cool. And if this gets smaller, hey, Alex, since you got your calculator out,
Yep.
could you find that one for me, please? And you got it in the right mode?
Wouldn't it be 0.0009?
Yeah, it's 3 zeros. And then six.
Oh,
Oh, and
okay.
it's way more nines now.
Way more nines, I'll take
It's
that.
9, 1, 2, 3, 4 nines. It's
How many?
6 nines.
I got the
and
exact
8.
same answer
Yeah, fantastic.
with adding one more zero.
With adding one more zero.
Oh, you had 5 nines in your top.
You got this?
I have 6
Adrian?
nines on the or 0.001.
Presumably my calculator just rounded. But
Yeah, definitely. Calculators are weird things. Let me tell you something. Doing math on a computer or a calculator is a weird thing because there's a class we teach here called numerical methods. Highly recommended if you're going to be a math major, you're ever going to do anything with a computer. Because computers are really bad with math. They're so bad that if you take a computer, like if you worked in a programming language like Python and you added 0.1 plus 0.2, you do not get the same thing as if you add 0.2 plus 0.1.
Why is that?
Because of the way they store these numbers. They can't store them precisely because a computer really only knows these are base 10. Computers work in base 2 binary. And when you convert these numbers into binary, it's an imperfect conversion. And so when you add these in two different numbers, it actually gives you, they're hella close, but they're off by like 10 zeros down.
So you can truncate it, right? Like you just get the right value.
Yes. Yeah, exactly. If you truncate, then everything's
Yeah.
going to be A-okay. Yeah, oh, I see what you mean. They store, yeah.
Yeah.
When they store these decimals as binary numbers, they have to truncate and they throw away tons of info. Yeah, exactly. Well, I didn't
Would it
see
be
that.
very complicated to put it in the 10 base language versus binary like
Well,
C++?
I don't- Yeah, I mean, I don't know how you would do that because in the end, a computer's just fancy switches. So in some ways, all a computer can ever understand is on and off at its most fundamental level. So anything you put on to have it act like it understands base 10 is just acting. It's just pretending, and you'll still end up with anomalies like that. It's kind of weird and kind of cool. Depending on who you are, the coolness factor
So the solution is just to
changes.
do all math by hand if you really want to.
Absolutely, 100%. That's right. Never fly to space, which is amazing, right? We can land on an asteroid. So that class, numerical methods, is all about this is true. How do we even do calculus? How do we land on an asteroid? How do we do anything? How do we freaking do anything? And we do. We manage. We manage. Let's take a look. Here's a problem for you, my friends. Limit as x goes to 2 of x to the 5th minus 32 over what? X cubed minus 8. Please find that limit. Using Lhopitals Rule.
We shouldn't even try plugging in sugar.
You should not. You probably should,
It's a waste of time.
but I'll make sure that that becomes folly soon. You'll wish you had. Yes, ma'am.
For notation, do you want us to just put like the LH?
Yeah.
Or do
that's-
you want us to put like derivative of top and bottom?
Oh no, just just write that LH over the equals in the transition. Yeah, that's great. Speaking of powers of 2. Yeah. Just look right,
And then you just plug 2.
and then just plug in 2, or maybe do a little simplification first even, right? Because I could cancel out the x squareds. So if I wanted to, if you're really not interested in finding x to the 4th, you can pretty much get by with x to the 5th. You don't have to, so this is no Lhopitals here. And actually, look, I'm gonna bring that 5/3 out front. X 4th over x squared is just x squared. So that's 5/3 times 4, 20/3. The alternative is pretty unpleasant. Let me stop and make sure there's no questions on that. But the alternative is rough. The alternative is factoring these things. And like this one, you have a hope. This one you have a hope if you remember like all the stuff way at the beginning of the semester about Pascal's triangle and all those kinds of things. It's still pretty painful. But this I could factor. This I'm not sure I probably could. But, and you probably could too if you knew the formula. It's not easy. This is easy. This is lovely. Any questions on that one? Slick, right? So far it's super slick because it's like power rule. Yay. Let's check out some more examples. What about limit as x goes to 0? Natural log of 1 plus x, I'll help you out with that, over x. Sketch out natural log real quick. That's your natural log graph. So when I plug, do we see that I get natural log of 1 over 0, 0 over 0? See that? Yeah, so this is a 0 over 0 form. So you can Lhopitals, go forth and Lhopitals. No, I don't think I should do that. That would be bad. There's the next one. Is it okay if I erase left side? Anybody over here? Good, cool, awesome. Let's take a minute, rock these out.
Is this something new to you?
Let me look.
It does. Nice, just making sure.
Yeah, that's good. Oh, and by the way, I don't know if you saw the email, but as I come around to help you, I do have a mask. Nobody said they wanted me to have this on when helping them yet, but that doesn't mean that's true, so. I do have a mask with me. I think Alex is okay with it. I'm scared. You seem terrified.
Yeah.
Just almost perpetually. You seem like you're in a permanent state of fear. It's like,
Totally. That's why I eat vegetables.
that's right. That's right, me too.
Soul vegetables and carbohydrates.
Yeah. Perfect. Perfect. Now have fun with that one. Yeah.
So yeah, feeling good.
Okay, awesome.
Yep. Solid, solid. Copy of the test.
Oh, yeah.
Because I understand what I did wrong on everything, but.
Yeah, right. What were the originals? How did I get it to you? Oh, I put it in that chat.
Yeah.
Yeah.
Oh, I can just use that. Never mind.
Do you still have it?
Yeah.
If you don't, send me an email and I'll get it to you, okay? Yeah. Good question.
I forgot.
Yeah. Yeah, so this is the chain rule, right? This is sine of 3 of x. So we did the outside curve 3 times the derivative of the inside. This is the derivative of 3x. Make your thinking tomorrow. So it's, you set up a derivative line right there. So here's y equals 3x. What's the slope of that line? Yeah, that's the reciprocal. So that's the derivative. Okay, so 3x is 3. Okay. Yeah. Yeah. How we doing here? Carly? Oh, you're on this last. Oh, you're on that last one. Or, yeah, keep going. Yeah, cool. Good. How we doing for that? Yes, you are. Indeed, you are. Take a hard, sir. Looking good, man. Yeah, that's that's beautiful.
I didn't see the next one.
Oh, good, good, okay, all the others. Okay. How we doing? Ooh, I like all the notes, the post-it notes. You're not sure on that derivative on that, okay, that's good, I'm glad you checked it out. Sorry, this is making me nervous. Okay, cool. So, what's the derivative of sine? It's cos, those both go to cosines. Then that's cool, pulling out that 3, and that 7 like you're about to do for the chain rule, but yeah, those are coses. There you go. Oh, you doing all right? Oh, you're on last one, awesome. How you doing, Fred? Oh. Beautiful. Oh, what about that last one? I didn't see that guy. Oh yeah, that won't be a good one. You'll enjoy that because you got those right. Indeed. Nice. Get some vanishing point action going on. Yeah. So in the one on the left side of the board, if you started on that one, that will require multiple applications of Lhopitals rule. So when you go do that one, because it's definitely a 0 over 0, when you go to the next, after you L'Hopital it, you still have 0 over 0. You got to keep L'Hopitaling until you don't have 0 over 0. Or convince yourself that that's never going to change, but it'll change. So that one that needs definitely at least 2 applications of L'Hopital's rule. Oh, or yes. You're probably like, oh man, this is bad. So you just keep taking the derivatives of the previous version you had.
Did we negative sign X? On top.
Yes, thank you. Yep, thank you. Your commission check will be in the mail. So no more L'Hopitals, so because now we've got 0 over -4. So this is just 0 over -4. Dead. Keep stop. Make sure everybody's with me. Any questions, any troubles? One, sir.
So it's actually 0.
Yes. Wait, so say more.
Okay, so we're good.
Okay, so so let's go through it. Plug in 0, the limit point. I get 0 over 0. You cool with that?
Yeah.
So I'd L'Hopital it. You cool with that as L'Hopitals?
Yeah.
Plug in 0 again, because I'm hoping that I get a plug-in chug. Plug in 0, I got cos of 0 is 1, I got 0 over sine of 0, 0 over 0 again. So I now apply Lhopitals rule as if this were my original problem. And when I take that derivative at the top, I get negative sine, minus plus 0, over the derivative of this, which is another 2 comes out because of the chain rule.
Yeah.
And I get negative 4 cos 2x. Plug again, sine of 0 is 0, cos of 0 is 1. So I've got negative 0 over negative 4 times 1.
Yeah, but didn't we said that like this, that there couldn't be a 0 on top or?
There could be a 0 on top, as long as there's not a 0 on the bottom as well. So okay, I'm glad you asked that. Yeah. So this over non-zero, this is great. That's always going to equal 0. Let me show you what's not great. So if I have this, that's L'Hopital. If I have non-zero over 0, I got problems. This is actually going to equal plus or minus infinity depending on, it depends on the circumstances. And so that takes a deeper analysis. Other questions? Those are great questions, those are an awesome question. All right, what do I got here? Okay, let's take a look at the new one. Let's talk about limits at infinity. So hopefully everybody's got that written down. And I want to write out what I just said so you see the terminology for this. Limits at infinity. Let's just talk about this in general so you have a sense of what the hell's happening, because we haven't really discussed this in any way, in any significant way. So we say the limit as x goes to infinity of some function equals L. If I write that, what that means is that the larger x gets, the larger the input gets, the closer the output gets to L. So that is a circumstance that means the graph looks like this. Here's L as an output. The graph is doing something like this. So there, you would call that a horizontal asymptote in that case. Or it could be like this. Or it literally could do that thing that I had at the beginning, where it's not necessarily an asymptote, it's more of an equilibrium state. So if I had L like this, think of some sort of pendulum oscillating, losing energy, settling to an equilibrium state. That would be 0, or whatever that position is right there. But that's the kind of behavior I'm talking about. Something settling down as time goes on. And this is literally an equilibrium state. If you're a scientist, that's what we're talking about. So you've got like the temperature of an object. Let's talk about where this could be. If I have some temperature function of some object, temperature at time t, and I look at the limit as t goes to infinity, this is the equilibrium temperature. If this is temp at time t. So for example, I for some weird reason, brought a hot potato along with me in my bag over here. It's all wrapped up in foil, and I pop out the hot potato and I set it on that table there. That temperature of that potato will do this. And this is room temp right here. Yeah? It will gradually come to room temp. If I have a nice chilled beverage in there and I set it on the table, it will do this. Its temperature will rise slowly as it gradually achieves room temperature, the ambient temperature. So this isn't just weird math fantasy. I mean, it is that too. Math fantasies are wonderful. They're my favorite fantasies, especially the fantasy of infinity. Some other day. Some other day we'll hear tales about infinity. Not today, we got business. So, that's what I mean when I talk about limits at infinity. Let's look at an example here. Consider, they don't always exist. Let's check out that. Let's think of a sine graph. What does a sine graph do as its input becomes larger? Does it ever settle down?
No.
Never, right? That doesn't settle down. There's no behavior like this or this. That never settles down. So this actually does not exist because sine of x never settles down. Settles on a value. Settles near a value. So this limits, they don't always exist. Let me give you a couple other possibilities for what these limits can do. You can also have the following circumstance, and let's just do this by picture. I could have the limit of a function at infinity be infinity. And what this means is that as x gets larger, the function gets larger without bound. It never settles down on anything. So that's something like this. As I move out this way, I continue to go out up this way.
But since it's a curve, wouldn't it eventually approach like completely vertical, the tangent line? Whereas if it was just a perfect diagonal line of 45 degrees, that would be infinite.
Well, where would it be going? So, first off, I love that question. Let's just start with that. But you're saying something like this, Alex. The thing you're thinking of is a vertical asymptote, right?
Yeah.
So you're saying something like this.
Yeah.
Now, in this case, it's still blowing up. The output is blowing up, but I'm approaching a finite spot. So a picture like this.
Yeah, but since it isn't a straight line, since it's a curve,
Yeah.
it's going to keep on curving to a point. Like
But
just
where's it going to end?
visualizing.
So tell me what the limit would be. What's the top value? So here, let's look at the favorite curve that looks like this.
What's the top x value?
Yeah. What does x squared cap off at?
Like, it's infinite, correct? Yeah. But I'm just saying what about the tangent line isn't infinite though?
That would also be infinite.
Really?
Yeah. So I mean, what is the tangent line of x squared? This is great. What is it?
2x.
2x. What happens as x gets bigger? So when x is 1 billion, what's the output?
Double.
2 billion. It never caps off. So the bigger x gets, the bigger the output gets. And that's what this means here. Yeah. Don't think of infinity as some point in a particular corner of the plane.
Yeah, I'm not saying it's infinite.
Yeah,
But
yeah.
I'm saying the shape of the line with it not being diagonal. I mean, I understand.
I think I know what you're thinking. I think I actually know what you mean. And
Like in the physical world,
yeah.
you know, like if I'm in say I exist in a finite space, like a square like this, right? If I want to maximize, like say I'm starting at the bottom left-hand corner, and if I want to maximize the distance I travel, I'd do a perfect diagonal line. That's the
Yeah.
longest route.
Absolutely.
Right? But if we do a x squared kind of line, then it's, you know, I mean, I guess that is a route to the corner, but I'm just thinking it was tighter. You know what I mean?
You can think of, here's a neat way to think of the plane. This is way beyond the scope of this class, but it's a cool thing to think about. It's something that I really dug thinking about when I was a math student. So let's picture the plane. Imagine that the plane, here's the plane that we always sketch in, but imagine it is a thing we can actually visualize. Right? Here's the y-axis, here's the x-axis, like this, and I'm making that fuzzy out there. Imagine I could get to infinity. And maybe it even looks a little rounder than that. Something like that. So imagine that edge there is infinity. And imagine that this is a flexible thing right here. It's like kind of a piece of rubber. If I grab the edges, if I could reach to infinity and grab the edges of the plane and start pulling them up, maybe into something like this. And then let's see. Yeah, so here's that y-axis, here's that x-axis again. So I'm forming it into a bowl. Yeah, and then I start pulling the top of the bowl, I'm cinching it together so that I've got something like this. Here's that little disc, I'm starting to shrink it, and it's like this. And then here's the outside, here's the y-axis, here's the x-axis. And then just close that all off at the top. And you end up, you can think of the plane in some ways as a sphere with a tiny little point at the top that's called infinity. Think of that as maybe the x-axis, that's the y-axis. But what I guess I'm trying to say here, Alex, is that all routes upward eventually take you to that place called infinity. Yeah. Anyway, that may have just amused myself, I don't know. Hopefully it hurt a little bit in like that good mathy hurt way. I love that idea. Okay. So
So if you
anyway,
walk
geez.
in any direction, you'll eventually reach a pole unless you're walking perfectly on the equator.
Exactly. Damn. Yes. Exactly. Beautiful. Nicely said.
Long enough.
Long enough. You will reach a pole. Even if
It was
even-
0.01 degrees.
Yeah. You walk on the equator, you diverge from it just a little bit. Right. You're right. Yep. We'll get up there. Slowly. Slowest damn way to the pole. But yep, takes you up there. That's cool. That was a great observation. What the hell were we doing? Okay. Right, I was looking at all the possibilities. So this is limit as x goes to infinity of f of x equals positive infinity. Limit as x goes to infinity of f of x equals negative infinity. Can you draw a picture for that? On your page, what would that look like, or in your mind? What does a graph look like if this happens? Unless I say it out loud yet, just think, give everybody a chance to like visualize. Practice visualizing and grasping. I feel like Juan's got us all like a slight head nod or something, maybe. No? Okay, now I saw a nod. Yeah, yeah. Yeah, what? Off the cliff, right? Yes. So this would look something like this. Keeps on cruising. Further out I go this way, further down I go that way. So, limit as x goes to infinity of negative x squared would be negative infinity. All right, infinite limits, let's see. We'll probably run across some weird stuff as we go. But let's get some fundamental knowledge out here. Some fundamental facts that we need. These should be in your tool belt. Your calculus tool belt. I would like you to fill these in. And I'm going to toss something a little tricky in here. What does that mean?
Is it just that way on the axis?
Left. Just keep cruising left. This means right, this means left. And then one more. What are those quantities? I don't have anything to drink in here. certainly the graph of e to the x should be right at the forefront of your thinking. Yep. This one will be a little trickier. Tossing in some more advanced things, just slowly and sneakily. I think we already had the graph log up, so I don't need to pop that back up. Can somebody help us out here? What's
It'll just be infinity.
positive infinity? Do we agree with that? It keeps blowing up. E to a bigger and bigger number is a really bigger and bigger number. So that's what we mean when we say this. You can get this as big as you want by getting this as big as you want. Output as big as I want by making input as big as I want. What about this one?
Just in the opposite directions of negative infinity.
Nope.
Zero.
Zip. That's what the height. So look at the output, right? What is the output approaching? The output is shrinking. As x approaches negative infinity, this is like a negative exponent. So if on your calculator you typed e to the negative 100, it would die. Probably, because it can't handle that. But that's just 1 over e to the 100. That is a huge number. I'm not sure there's that many molecules in the universe. I'm not sure how many there are. I don't think anybody knows, but zip, as it shrinks out this way, it's a horizontal asymptote to the left. What about this one? 0. This is really important, and there's the graph, you can look at it, but I want to talk about this because in general, there's a more general version of this that I want you to know, and that is if I have a limit and the top is fixed, roughly, essentially constant, but the bottom is blowing up, getting bigger and bigger. That limit is essentially 0. And this thinking here that the top is fixed, so I've got like 17 over a billion. And then I could get 17 over 100 billion, 17 over a Google. You know what a Google is?
It's like 16 zeros or something.
Oh, more. What's a Google? Not the dumbass Google that owns everything, not those bastards. The number. Anybody know what this number is? It is a 1 followed by 100 zeros. The person who wrote this number down asked their little kid to name that number, and this was the name that it got. Yeah, for real, that's the real story. A Googleplex is a 1 followed by this many zeros. That number, I don't even know how big that number is, but this is equal to a 1 with a Google number of zeros.
So hypothetically, when we're doing math with an exponent greater than 80, it's all fucking theoretical and useless.
Yeah, that sounds about right.
Okay.
That's precisely said. Yes. But this fact here is what I really want you to know. This is going to get you far, knowing that if the top of a quantity is fixed but the bottom is blowing up, it's going to 0. So let's get a little bit more. I know I can sense that you want to go. I know you want to go. Let's do one more thing. In the case that I'm doing, limit as x goes to infinity of a ratio. and this ratio ends up as 0 over 0 or infinity over infinity, I can apply Lhopitals Rule. So if 0 over 0 or infinity over infinity, we can apply Lhopitals Rule. And then in this case, this would equal the limit as x goes to infinity of the derivative ratio. So for example, if I have the limit as x goes to infinity of 3x to the 7th minus 2x squared plus 1 over, let's work with a number we've already had, 7x to the 7th plus x to the 4th. There might be a little discussion in this, just a little bit. So now we're trying to think. What you can do is essentially like plug in infinity. And that's a weird idea. But you can imagine when these x values are really big. So when you see infinity, infinity isn't a place. It's an aspiration. This isn't a place we can go. This just means we're getting bigger without bound. So you can always replace x with a really big number. When x is a really big number, say like 10 cubed, that's not even that big, it's only 1,000. But when I plug it in here, notice that this would be 3 times 10 cubed to the 7th minus 2 x cubed squared plus 1 over 7 10 cubed to the 7th plus 10 cubed to the 4th.
Why'd you do x cubed on the top? Why didn't it just be 10 cubed to the right? And then 2x.
Oh, thank you, Alex. Yes, sir. You were right. Yeah, is that better?
Sure.
Thank you. Yes, thank you. Yeah, I just replaced this x with 1,000, essentially. But you simplify this quantity, let me get over here. What do we get? Well, properties of exponents say that's 21, so that's 3 times 10, that's 3 times 10 to the 21st, minus 2 times 10 to the 6th plus 1, all over 7 times 10 to the 21st, plus 10 to the 12th. These numbers in front, these numbers dominate everything else. This number in front, this 10 to the 21st dominates all this stuff. So if you actually sketched out the graph of that top thing or that bottom thing, what you'd see is that eventually they're both flying off to infinity. The top is getting bigger without bound, and the bottom is getting bigger without bound. But more importantly, look at what matters here. If you were doing these computations, first off, your calculator's going to barf on this. It's going to have to go to scientific notation. And then when you start subtracting stuff off, this is a pittance compared to that. If you have this many dollars, if Joey in his ETH mine have made 10 to the 21st dollars by the end of the semester,
That's more money than's ever existed.
that's probably more money that's ever existed. And so Joey is going to be quite happy to toss me 10 to the $6, right? He'd toss me 10K. Or what is that? No, that's more, it's $1 million. He can give me $1 million. He won't even notice it. Okay, thanks. Yeah, he'll just give me whatever I want. Because it won't even touch this quantity here. And then down here, and then somebody wants to give Joey, he's got this out of his ETH mine, somebody gives him 10 to the 12th, he's like, I'll take it or leave it, it don't really matter. I literally have all the money that's ever existed or ever could exist. So sure, give it to me or keep it. Either way, these numbers don't matter. What matters out in front. So this ratio is essentially what? 3 to 7. We would expect this quantity here to be dominated by the behavior of these two terms. And we can prove, using Lhopitals Rule, that that limit is literally 3/7. Now I'm going to do it with Lhopitals Rule, and then we're going to call it a day. So notice that the top is going to infinity, the bottom is going to infinity. So I can L'Hopital, and I get limit as x goes to infinity of take the derivative of the top. Derivative of the bottom. What's the top doing as x gets bigger?
It's getting bigger.
It's getting bigger, right? Look at these main terms. X to the 6th versus x? Are you kidding me? This shit don't matter. So this is still an infinity over an infinity form. So I can L'Hopital again. I take a limit.
You just do that to get rid of all the shit on the right.
Essentially, I'm doing that until something comes up that makes life easy for me. So I think I'm gonna regret this.
Here, I'll calculate it. 21
Thank-
times 6 is 126. And 49 times 6
Oh, God.
294.
294 x to the 5th, and I got this one.
You can do 12.
I got that one. And so again, infinity over infinity. If this doesn't make you want to leave, I don't know what will. This is what you do at the end of the party when your guests are hanging out too long.
630 x to the 4th.
Okay, so hold on. So wait,
630 x to the 4th.
minus 0.
And 294 times 5 is 1,470 x to the 4th.
1,470. 470.
X to the 4th.
X to the 4th plus 24. X, keep me going, Alex.
Okay, we
Got still infinity over infinity.
630. That's okay. So on the top you got 2,520 x cubed, and then 1470.
We're almost done. We're almost done.
What is that? 1470 times 4. So you got 5,880 to the 3rd.
Plus 2. Last time.
Okay.
Last time, my friend. It's still infinity over infinity.
7,560 x squared, and then that's gonna be 17640 x squared.
X squared.
Yep.
Beautiful. Yeah. So, hey, look. Now there's no pluses, so I can cancel. Yay. So the final answer is 7,560 over 17,640. What? I thought I said it was going to be
3/7.
3/7. What happened?
I don't know.
Yeah, I do.
What happened?
Well, somebody tell me. Gotta cancel. We gotta simplify, right? So if I simplify this fraction, if I have, then they still haven't left the party. You're yawning, you're doing all your yawning, you're like looking at your watch, still not out, even after this. Then you say, well, I guess we need to factor these. That'll get rid of them. And what you'll find out is that this would simplify to 3 sevens.
Yeah, it does.
Excuse me. Cool, thank you.
1.4285714.
Beautiful, thank you. That's enough.
There's something wrong with the calculator. I was like, no.
Online, Friday. Online. Same link as always.
So we could just take the coefficient, basically, if it's a big exponent like that.
Yes. Yeah, we'll talk about that. Yeah, that's the general rule of thumb.
So math is all fake.
Math is complete lie. I'm glad that's what you got out of
It's just
all
a
this.
way they make money off of college students.
And Juan's already got his corrections.